Welcome to our 5-episode video series about the Antikythera Mechanism.
Wait, what can be so fascinating about 82 tiny fragments found in an age-old shipwreck that you'd need 5 episodes?
In this video series, we are going to take an interdisciplinary approach to sum up what is known about the object known as the Antikythera Mechanism, trying to answer questions like, how do we know that these fragments were once part of an astronomical device? What could that device have been used for? Why and how was it constructed?
We will also share with you how we built our own replica, so let's dive in.
We are quite literally diving in. Derek de Solé-Price tells the story of the discovery of the shipwreck, in which fragments of the mechanism were found, in his article Gears from the Greek.
Shortly before Easter of 1900, a party of sphenagrads, sponge fishers from the island of Syme near Rhodes in the Dodecanese, left their normal fishing grounds in the Tunisian waters of North Africa and began to sail east towards home. Driven off course, they sought shelter near Port Potamo on the almost uninhabited, rocky and barren islet of Antikythera, which lies just midway between the two larger islands of Kythera and Crete, splitting the channel between them and creating an infamously dangerous graveyard for shipping, ancient and modern, a place of sandbars, shoals, and sudden currents. Safe after the storm, they decided to explore the shallow rock shelf below them in the hope of finding sponges. Going to a depth of 140 feet, or 42 meters, one of the divers, Elias Tediatis, found to his utter astonishment that a great ship lay wrecked on the bottom.
This wreck later became known as the Antikythera wreck. The ship is estimated to have sunk around 80 to 50 BC thanks to other ancient Greek objects found in it. In 1901, the first excavations were conducted, and objects were recovered, among which fragments of a mechanism. As there were also many statues, pottery pieces, and other objects to be catalogued, these fragments were only identified a year later in 1902, when Zvornos published the first account of their inscriptions. Later, attempts were made to date this unique object, with evaluations ranging from 250 BC to 86 BC. More recently, many replicas were produced,
Including one in Legos.
Let's look at what exactly is displayed by the mechanism. There is one large dial at the front and two at the back. The front dial is what we're going to explore now in our astronomy section.
Imagine, you're looking up at the sky and this cloud drifts by. Doesn't it look like a fairy dragon? You stay long enough that now you're looking at the night sky, at a time where light pollution was unheard of, and the only sound disturbing the night is that of cicadas. You see all these stars, and your imagination starts to meander again. These 13 brilliant stars, they remind you of the scorpion that you encountered on your way here. And over there, it looks like the centaur from your teacher's story comes to life.
These patterns in the night sky are constellations. In ancient cultures, it was common to associate a mythological story with a group of stars to tell how it found its way to the sky. For example, Taurus is related to the Minotaur. A special set of constellations is the zodiac. These 12 symbols that compose it in the Greek tradition are the ones we still know in the Western world today.
Starting with Aries, then Taurus, which we already looked at, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and finally Pisces.
They were, and still are by some, considered to have astrological significance. But their importance is also linked with an astronomical manifestation, the ecliptic. The ecliptic can be thought of as a reflection of the Earth's motion around the Sun. From the viewpoint of a terrestrial observer, i.e. you and me, what we can see is the Sun's path through the constellation. So the ecliptic is this path, and the zodiac constellations are the ones along this path.
Of course, this observation is prevented by the fact that the sun is so bright that during the day we can't see any other stars behind it, and that It is heading by the horizon at night, so the constellations we see at night are the ones opposite to where the sun lies on the ecliptic.
For example, if you're born in the first half of September, your star sign will be Virgo. But you won't see this constellation in the sky on your birthday. It will be visible 6 months later, in March.
In the Antikythera Mechanism, it's the terrestrial point of view that's shown in the front dial. As you turn the handle, which makes time advance, so to speak, a pointer representing the sun moves through the zodiac constellations, following the ecliptic.
As well as the zodiac signs, there is an outer scale with the Egyptian calendar, 12 months of 30 days and an extra 5-day period, so a 365-day year, which the pointer of the sun goes through simultaneously. It must be noted that the outer scale could be manually adjusted to compensate for leap years. Now we're going to look at how this and other astrophysical cycles were actually materialized in the mechanism by studying its engineering features. Let's start with the basic building blocks of a mechanism: gears. Gears are used to transmit rotational motion. In simple terms, one gear turning will cause its neighbor to turn. The first ones were probably made out of wood, as suggested by Chinese writings, about 800 BC.
Nowadays, we use many different types of gears. The simplest one is cylindrical gears, with straight teeth parallel to the axis, the so-called external spur gears.
These are the ones used in the Antikythera mechanism.
In a system with two such gears, the larger wheel is called the gear and the smaller one the pinion. Note that if the pinion turns clockwise, the gear will turn anti-clockwise, and vice versa. Another important feature is the gear ratio, the number of teeth on the driven gear divided by the number of teeth on the driving gear. For instance, if the driving gear has 20 teeth and the driven gear has 60, the ratio is 3:1, and the driving gear has to turn 3 times for the driven gear to rotate once. So-called idler gears are placed between two gears, don't change their gear ratio, and the driving and driven gears will turn in the same direction.
The gear ratio is what's used in the Antikythera mechanism to represent astronomical cycles. There is only one input for the 3 dials and many more pointers. To achieve this, there are notably two 53-teeth gear, and 53 being a prime number, these gears must have been quite hard to manufacture.
In our replica, we use 35 gears, according to this theoretical model by Freeth and Jones. You can clearly see the gearing paths that lead to each of these 3 dials. As mentioned before, it's the specific gear ratios that make the different pointers turn respectively to each other.
In this episode, we looked at the discovery of the mechanism, studied parts of the front dial, and gained an understanding of the technology involved with fabricating such a complex object. In episode 2, our investigation will turn to ancient Greek science, planetary motion, and answer the question, how on earth can we know from these 82 tiny fragments what the fully functional mechanism looked like? So, stay tuned!